Hello there, and welcome to the Sleepy Library. Tonight, we are going on a journey to the very edges of existence itself, or perhaps to places where edges do not exist at all. We are going to explore one of the most profound questions that has ever stirred the human imagination. Does the universe go on forever, stretching endlessly in all directions without boundary or limit? Or does it have an edge, a final frontier beyond which nothing exists? This is not a question with a simple answer, but rather one that invites us to contemplate the nature of space, time, and reality in ways that stretch our minds while soothing our curiosity. So, settle in, get comfortable, and let your thoughts wander through the cosmos. There is no rush. The universe has been here for nearly 14 billion years, and it will be here long after we close our eyes tonight. Let us begin this gentle exploration together. Before we venture into the deep questions about the universe's boundaries, let us start with something familiar, something we can wrap our minds around more easily. Think about the last time you stood outside on a clear night, far from city lights, and looked up at the sky. The darkness above was punctuated by thousands of points of light, each one a sun burning across incomprehensible distances. Some of those stars are relatively nearby, galactic neighbors just a few light years away. Others are ancient giants whose light has traveled for thousands of years to reach your eyes. When you look at the night sky, you are not just seeing points of light. You are witnessing a three-dimensional tapestry of cosmic architecture spread across space and time. That faint band of light stretching across the darkness is the Milky Way, our home galaxy, seen edge-on from our position within one of its spiral arms. Those smudges that are not quite stars, if you look carefully, might be nearby galaxies, entire islands of hundreds of billions of stars, so distant that their collective light blends into a soft glow. The human eye can see perhaps 3,000 stars on a perfectly dark night, maybe 5,000 if conditions are ideal. But our galaxy alone contains somewhere between 200 billion and 400 billion stars. And our galaxy is just one among an estimated 2 trillion galaxies in the observable universe. Each of those galaxies contains its own multitude of stars, many with planets, some perhaps with moons, all scattered across a space so vast that even traveling at the speed of light, the fastest possible speed in the universe, it would take billions of years to cross from one edge of the observable cosmos to the other. When we look up at the night sky, we see stars scattered across the darkness, like diamonds on velvet. Each tiny point of light represents a sun, perhaps with planets of its own, existing at distances so vast that our minds struggle to comprehend them. The light from some of these stars has traveled for hundreds or thousands of years just to reach our eyes. We are literally seeing the past when we gaze upward, witnessing light that began its journey long before we were born. Let us pause for a moment and truly consider what this means. When you look at a star that is 1,000 light years away, you are seeing that star not as it is now, but as it was 1,000 years ago. The light that touches your retina left that distant sun around the time that medieval castles were being built on Earth, when humans had no concept of what stars truly were, when the very idea of vast cosmic distances would have seemed like madness or heresy. If that star has planets orbiting it, and if those planets harbor life, and if that life has developed technology to look back at us, they would not see our present. They would see Earth as it was 1,000 years ago. They would see our planet with different continents of ice, different configurations of civilization, different stories unfolding on the surface. The present moment, as we experience it, is not a shared experience across the universe. The concept of now depends on where you are and what you can see. This is not just philosophical musing. It is a consequence of the finite speed of light, one of the most fundamental constants in physics. Light travels at approximately 186,000 miles per second, or about 300,000 kilometers per second, if you prefer metric. This seems impossibly fast by human standards. In a single second, light can circle the Earth more than 7 times. Yet, on cosmic scales, light is almost painfully slow. Consider our Sun. It sits at the center of our solar system, a glowing ball of nuclear fusion that has powered life on Earth for billions of years. The light from the Sun takes about 8 minutes and 20 seconds to travel the 93 million miles to Earth. This means that when you see the Sun in the sky, you are seeing it as it was slightly more than 8 minutes ago. If the Sun were to suddenly vanish, we would not know it for over 8 minutes. We would continue to receive its light and warmth, completely unaware that our star had disappeared, until that final wavefront of photons reached us and the light switched off. Extend this principle outward. The nearest star system to our Sun is Alpha Centauri, about 4.3 light-years away. If we could somehow send a message to inhabitants of a planet orbiting Alpha Centauri, and if they responded immediately, the total round-trip time for the communication would be more than 8.5 years. A simple conversation spanning the nearest stars would take nearly a decade. The distances grow more staggering as we venture further. The center of our Milky Way galaxy lies approximately 26,000 light-years away. The light we see from the galactic core tonight left that region around the time that humans were painting on cave walls in Europe, when mammoths still roamed the Earth, when our species was just beginning to develop complex language and culture. The Andromeda Galaxy, our nearest large galactic neighbor, sits about 2.5 million light-years distant. The light we see from Andromeda tonight began its journey when our earliest human ancestors were first emerging in Africa, when the evolutionary story of our species was just beginning to be written. The photons that enter our telescopes from Andromeda have been traveling through the void for longer than our genus has existed. But what lies beyond the stars we can see? If we could travel faster than light itself, if we could journey past every galaxy, every cluster of galaxies, every structure we have ever observed, what would we find? Would we eventually reach a wall, a boundary, some cosmic shoreline where space simply ends? Or would we find that space continues forever, an infinite expanse with no beginning and no end? These questions have puzzled philosophers and scientists for millennia. The ancient Greeks contemplated infinity with a mixture of fascination and unease. Aristotle argued that the universe must be finite because infinity was too troubling a concept to accept. He reasoned that if space went on forever, how could we make sense of position or place? Others imagined that if the universe had an edge, what would happen if you reached it? Could you stick your hand through? Would you encounter a wall? And if there were a wall, what would be on the other side of it? The paradox presented by these questions reveals something profound about the human condition. We are creatures bound by boundaries. Every room we enter has walls that define where inside ends and outside begins. Every journey we take has a point of departure and a destination. Every book we read, every song we hear, every conversation we have possesses a beginning and an ending. Structure, limitation, and finitude are woven into the fabric of our daily experience. Yet, when we turn our thoughts to the cosmos as a whole, when we attempt to conceive of the totality of existence, these familiar concepts begin to break down. The universe, in its magnificent indifference to our intuitions and expectations, may operate according to principles that transcend our everyday understanding. It may be that the very concepts of boundary and edge simply do not apply on the largest scales, not because there is something beyond the boundary, but because the question itself is based on assumptions that do not hold in the cosmic context. This is not the first time in history that humans have had to radically revise their understanding of space and scale. For most of human history, we believed that Earth was flat and finite, with edges beyond which one might sail and fall into oblivion. The idea that Earth could be a sphere with no edge seemed counterintuitive. How could people on the bottom not fall off? How could water stay on a curved surface? These questions made sense within a limited framework of understanding, but became irrelevant once we grasped the true nature of gravity and spherical geometry. Similarly, for centuries, humans believed that the stars were fixed lights on a celestial sphere that rotated around Earth. The universe was small, perhaps extending just beyond Saturn, the most distant planet visible to the naked eye. The idea that stars were other suns scattered at vast distances through space would have seemed absurd. The scale was simply too large to conceive, the implications too radical to accept. Each revolution in our understanding has made the universe larger, more complex, and stranger than we previously imagined. And now, we face perhaps the ultimate question of scale. Is the universe itself finite or infinite? Does it have an edge or not? The answer, as we will explore, depends on subtle features of cosmic geometry and topology that can only be measured through careful observation of the deepest structures of space and time. Let us start with what we can observe directly. Our observable universe, the portion of the cosmos from which light has had time to reach us since the beginning, extends about 46 billion light-years in every direction from Earth. This creates a sphere around our planet that is roughly 93 billion light-years across. Within this vast bubble, we find approximately 2 trillion galaxies, each containing hundreds of billions of stars. The numbers are staggering, almost incomprehensible. But here is something that might surprise you. The observable universe is 13.8 billion years old, yet it extends more than 13.8 billion light-years in radius. How is this possible? If light has been traveling toward us for only 13.8 billion years, should not the most distant objects we can see be only 13.8 billion light-years away? The answer lies in the expansion of space itself. The universe has been expanding since the Big Bang, and the fabric of space has been stretching all along. When light from a distant galaxy was first emitted long ago, that galaxy was much closer to us than it is now. Over the billions of years it took that light to reach us, space expanded, carrying that galaxy far away. The result is that the galaxy which emitted the light we see is now much further than the simple calculation of light travel time would suggest. Imagine you are standing on one spot of a huge rubber sheet, and someone else is standing on another spot some distance away. They shine a flashlight toward you. While the light is traveling across the sheet, someone begins stretching the sheet in all directions. The light continues moving across the surface, but the surface itself is growing. By the time the light reaches you, the person with the flashlight has been carried much further away by the stretching of the sheet. This is analogous to what happens in our expanding universe. The expansion of space means that the most distant galaxies we can observe, those whose light was emitted shortly after the Big Bang when the universe was young, are now located about 46 billion light-years away, even though their light has only been traveling for 13.8 billion years. The space between us and those galaxies has been stretching all along, increasing the distance while the light was in transit. This 46 billion light-year radius defines the edge of our observable universe. It is a horizon, a boundary beyond which we cannot see, not because there is nothing there, but because light from beyond that distance has not yet had time to reach us. Every moment that passes, this horizon expands a tiny bit. Light from previously unreachable regions finally completes its journey across the cosmos to our telescopes. We see deeper into space, which means we see further back in time, witnessing the universe as it was in its youth. But here is the crucial insight that shapes our understanding of the question at hand. This observable horizon is not a physical edge to the universe itself. It is simply the limit of what we, from our particular location in space and time, can possibly observe. An observer in a galaxy 45 billion light-years away would have their own observable universe, centered on their location, extending 46 billion light-years in all directions from them. Their observable universe would overlap with ours, but it would also extend into regions we cannot see, regions forever beyond our cosmic horizon. The observable universe has an edge, but that edge is not a physical boundary. It is simply a horizon created by the finite speed of light and the finite age of the universe. Light travels at approximately 186,000 miles per second, which sounds incredibly fast, and it is by any earthly standard. A beam of light could circle the equator of our planet more than 7 times in a single second. It could travel from the Earth to the Moon in just over 1 second. It could reach Mars in a matter of minutes when the planets are favorably aligned. Yet the universe is so vast that even at this tremendous speed, light from distant regions has not yet had time to reach us. Think about what this means. There are galaxies out there, billions of them, whose light is currently traveling toward us through space, but has not yet arrived. In 1,000,000 years, if humanity or its descendants still exist and are still watching the sky, they will see galaxies that are invisible to us today. The observable universe of the future will be larger than the observable universe of the present, extending further into space and further back in time. But here is a curious and somewhat melancholy fact. While the observable universe is growing because light from more distant regions continues to arrive, the universe is also expanding at an accelerating rate. This means that there are galaxies whose light will never reach us, no matter how long we wait. These galaxies are so far away, and the space between us and them is expanding so rapidly that the light they emit is being carried away from us faster than it can travel toward us. They lie beyond what cosmologists call the cosmic event horizon, a boundary that separates the regions of space we can potentially observe from the regions that are forever beyond our reach. Every moment, as the universe expands, more galaxies cross this event horizon, disappearing from view. Not because they are being destroyed, but because the expansion of space carries them beyond the realm of possible observation. In the deep future, trillions of years from now, most galaxies will have receded beyond this horizon. Observers in our galaxy, if any exist, will look out and see only darkness beyond the local cluster of gravitationally bound galaxies. The rich, galaxy-filled universe we observe today will have faded into emptiness. Not because the galaxies ceased to exist, but because the expansion of space carried them away faster than their light could reach us. This might seem like a digression from our central question about whether the universe has an edge, but it is deeply relevant. The observable universe clearly has an edge, a horizon beyond which we cannot see. But the universe as a whole, the totality of space and everything in it, may or may not have an edge. The observable limit is a feature of our perspective, not necessarily a feature of reality itself. But what about the universe beyond our horizon? This is where the question becomes truly fascinating, and where we must turn to some of the most profound insights in all of physics. Scientists have developed several lines of reasoning to address whether the totality of space is finite or infinite, and the answer hinges on some remarkable discoveries about the shape and structure of the universe itself. Discoveries that would have seemed like pure fantasy to scientists just a century ago. According to Einstein's theory of general relativity, published in 1915, space is not just an empty container in which things exist, like water in a glass or air in a room. Space itself is a dynamic, physical entity that can bend, stretch, warp, and curve in response to matter and energy. The presence of mass literally warps the fabric of space around it, creating curvature. And this curvature is what we experience as gravity. This was a revolutionary idea when Einstein first proposed it, overturning centuries of assumptions about the nature of space and time. Before Einstein, space was thought to be an absolute, unchanging stage on which the events of the universe played out. Newton's physics assumed that space was flat, infinite, and uniform, providing a neutral background for matter and forces to interact. Time, too, was thought to flow at the same rate for everyone, everywhere, regardless of circumstances. Einstein showed that this picture was fundamentally wrong. Space and time are not separate entities, but are woven together a single fabric called space-time. This four-dimensional fabric can be stretched, compressed, and curved by the presence of mass and energy. A massive object like the Sun creates a depression in space-time, much like a bowling ball placed on a stretched rubber sheet creates a dip. Smaller objects like planets roll along the curves of this depression, and we interpret their curved paths as orbits caused by gravity. But gravity is not really a force pulling planets toward the Sun. Rather, planets are following the straightest possible paths through curved space-time. They are moving in what are called geodesics, the equivalent of straight lines in curved space. From the planet's perspective, it is simply traveling forward, but the curvature of space-time around the Sun bends its path into an orbit. This insight revolutionized our understanding of the cosmos and opened up entirely new ways of thinking about the universe's size and shape. If space can curve, then the universe as a whole might have an overall geometric structure, a shape that determines its ultimate size and whether it has boundaries. The geometry of the universe on the largest scales became a question that could be answered through observation and measurement, not just philosophical speculation. One of the key questions scientists have pursued is, what is the overall geometry or curvature of space on the largest scales, far beyond individual galaxies or even clusters of galaxies? Is space flat on average, like an infinite sheet of paper extending in all directions? Is it positively curved, like the surface of a sphere? Or is it negatively curved, like a saddle or a Pringle-shaped chip? The answer to this question has profound implications for whether the universe is infinite or finite, and whether it has an edge. To understand this, let us think about two-dimensional surfaces, which are easier to visualize than three-dimensional space. Imagine you are a tiny, flat creature living on a two-dimensional surface, unable to perceive any third dimension. Your entire universe is this surface. Now, depending on the geometry of your surface, your universe would have very different properties. If you live on a perfectly flat, infinite plane, your universe has no boundaries. You can travel in any direction forever and never reach an edge. If you draw a triangle on this flat surface, the angles inside that triangle will always add up to exactly 180 degrees, just as you learned in school geometry. If you draw two parallel lines, they will never meet, no matter how far you extend them. This is Euclidean geometry, the familiar geometry of flat space. But if you live on the surface of a sphere, like the surface of the Earth, things are different. The surface is finite. You can measure its total area. If you travel in any direction long enough, you will eventually return to where you started, having circumnavigated the sphere. Yet there is no edge, no boundary to this universe. Every point on the surface is equivalent to every other point. There is no center, at least not within the surface itself. The center of the sphere exists in a third dimension that you, as a flat creature, cannot access or perceive. Moreover, the geometry itself is different. If you draw a large triangle on the surface of a sphere, the angles will add up to more than 180 degrees. You can see this easily if you imagine a triangle on Earth with one vertex at the North Pole and two vertices on the equator, separated by 90 degrees of longitude. Each of the three angles in this triangle is 90 degrees, so they sum to 270 degrees, far more than the flat space value. Similarly, if you draw two lines that start out parallel on the surface of a sphere, they will eventually converge and meet. Lines of longitude, for example, are parallel at the equator but meet at the poles. This is positive curvature, the geometry of a sphere. A positively curved universe would be finite in size but have no edge or boundary. It would wrap back on itself in a higher dimensional way that is difficult to visualize but mathematically well defined. Now, consider a third possibility: negative curvature, like the surface of a saddle. If you draw a triangle on a saddle-shaped surface, the angles will add up to less than 180 degrees. Parallel lines will diverge, moving apart as they extend. A negatively curved universe that extends infinitely would be infinite in size, with no boundaries. Space would stretch on forever, but it would be intrinsically curved in a way that affects the geometry of shapes drawn within it. So, the curvature of the universe determines whether it could be finite or infinite, and whether it has edges or wraps back on itself. But how do we measure the curvature of three-dimensional space? We cannot step outside the universe to see its shape from an external vantage point. Instead, we must make measurements from within, using the behavior of light and matter to infer the overall geometry. Scientists can measure the curvature of three-dimensional space by examining the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This radiation was released when the universe was only 380,000 years old, and it carries information about the geometry of the early universe imprinted in its subtle temperature variations. The cosmic microwave background is one of the most remarkable discoveries in the history of astronomy, and it provides our deepest view into the early universe. To understand what it is and why it matters, we need to journey back in time to the earliest moments of cosmic history. In the beginning, the universe was unimaginably hot and dense. In the first moments after the Big Bang, temperatures were so extreme that even atoms could not exist. Matter existed as a searingly hot plasma, a soup of elementary particles including protons, neutrons, electrons, and photons, all constantly colliding and interacting with each other. The photons, particles of light, could not travel very far before scattering off the charged particles in the plasma. The early universe was opaque, like being inside a thick fog where light cannot penetrate more than a short distance. As the universe expanded, it cooled. After about 380,000 years, the temperature had dropped enough for protons and electrons to combine and form neutral hydrogen atoms. This moment is called recombination, though that is actually a misnomer since the protons and electrons had never been combined before. When neutral atoms formed, something remarkable happened. The universe became transparent. Photons could suddenly travel freely through space without constantly scattering off charged particles. The light that was released at this moment has been traveling through the universe ever since. This ancient light, stretched by billions of years of cosmic expansion, is what we now detect as the cosmic microwave background radiation. Originally, the light was emitted with a temperature of about 3000 degrees Kelvin, glowing a warm orange-red color. But after nearly 14 billion years of expansion, the wavelengths of this light have been stretched by a factor of more than 1000. What was once visible light has been redshifted into microwave radiation, corresponding to a temperature of just 2.7 degrees above absolute zero. The cosmic microwave background fills the entire sky. No matter which direction you point a sensitive radio telescope, you detect this faint glow. It is remarkably uniform, showing almost the same temperature in every direction. This uniformity tells us that the early universe was extraordinarily smooth and homogeneous. But not perfectly smooth. There are tiny variations, fluctuations in temperature of only about 1 part in 100,000. These minute variations represent slight differences in density in the early universe, and they are crucially important because they seeded the formation of all the structure we see today. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter, which strengthened their gravity further in a feedback loop that eventually formed galaxies and clusters of galaxies. The patterns in the cosmic microwave background are, in a sense, a baby picture of the universe, showing the initial conditions from which everything emerged. The cosmic microwave background was discovered accidentally in 1964 by two radio astronomers, Arno Penzias and Robert Wilson, who were working at Bell Laboratories in New Jersey. They were testing a large, horn-shaped antenna intended for satellite communications when they detected a persistent background noise that would not go away. No matter where they pointed the antenna, no matter what time of day or night, the noise was there. They thought it might be interference from nearby New York City or pigeons nesting in the antenna. They even went so far as to clean out the pigeon droppings, but the signal remained. What Penzias and Wilson had discovered, though they did not immediately realize it, was the afterglow of the Big Bang itself. Other physicists had predicted that such radiation should exist, but the prediction had been largely forgotten. When Penzias and Wilson's finding was connected to this earlier theoretical work, it became clear that they had made one of the most important discoveries in cosmology. They were awarded the Nobel Prize in Physics in 1978 for their work. Since that initial discovery, successive generations of instruments have mapped the cosmic microwave background in increasing detail. In the 1990s, NASA's Cosmic Background Explorer satellite, known as COBE, created the first detailed full sky map of the temperature variations in the microwave background. These maps revealed the slight ripples in temperature that correspond to density fluctuations in the early universe. The variations were incredibly small, just a few millionths of a degree, but they were there, and they were precisely what theories of cosmic structure formation predicted should exist. In the early 2000s, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, which mapped the cosmic microwave background with much greater precision. WMAP operated for 9 years, producing a detailed picture of the microwave sky and allowing cosmologists to measure various properties of the universe with unprecedented accuracy. The mission determined the age of the universe to be 13.77 billion years, measured the rate of cosmic expansion, and determined the amounts of ordinary matter, dark matter, and dark energy in the cosmos. Most relevant to our question about the universe's shape, WMAP measured the geometry of space by analyzing the pattern of temperature variations in the cosmic microwave background. The idea is elegant. Those tiny hot and cold spots in the microwave sky have characteristic sizes that depend on the geometry of the universe. Sound waves propagating through the hot plasma of the early universe created these variations, and the scale of the patterns reflects how space curves or does not curve. Think of it this way. If the universe is positively curved, like a sphere, then the patterns in the microwave background would appear magnified, larger than they would in flat space. If the universe is negatively curved, like a saddle, the patterns would appear smaller. By carefully measuring the angular size of these features, cosmologists can determine the curvature of space. The results from WMAP, later confirmed and refined by the European Space Agency's Planck satellite, launched in 2009, show that the universe is flat to within measurement precision. The angles of a triangle drawn across the largest scales of the cosmos add up to 180 degrees, as far as we can measure. The curvature parameter, if not exactly zero, is extraordinarily close to zero, within less than 1%. Over the past few decades, a series of space-based telescopes, including the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and most recently the Planck satellite, have mapped the cosmic microwave background with extraordinary precision. These measurements have revealed something remarkable. As far as we can tell, the universe is geometrically flat to within a margin of error of less than 1%. This flatness has profound implications. If the universe is truly flat and extends infinitely in all directions, then it would be infinite in size. An infinite flat universe would contain an infinite amount of space and, presumably, an infinite amount of matter and energy distributed throughout it. There would be no edge, no boundary, no place where space ends. If you could travel in a straight line forever, you would never reach a wall or circle back to your starting point. You would simply journey through space eternally, passing through region after region of galaxies and structures that continue without end. Let us pause to consider what an infinite universe truly means, because the implications are both fascinating and somewhat unsettling. In an infinite universe, with matter distributed more or less uniformly throughout it, as observations suggest, every possible configuration of matter would not only exist, but would exist infinitely many times. The reason is straightforward. There are only so many ways that atoms can be arranged within any given volume of space. The number is vast, incomprehensibly large, but it is finite. Consider a cube of space, say, one that is 100 million light-years on a side. Within this volume, there are countless galaxies, stars, planets, and other structures. The atoms and particles within this region can be arranged in an enormous number of different ways, but that number, however large, is still finite. Now, if space extends infinitely in all directions, then there must be infinitely many such cubes. And if there are infinitely many cubes, each with a finite number of possible arrangements, then by sheer probability, every possible arrangement must occur, and must occur infinitely often. This means that somewhere, incredibly far away, far beyond our observable horizon, beyond the reach of our fastest spacecraft or our most powerful telescopes, there could be another region of space with atoms arranged almost exactly as they are here. There could be another Earth, orbiting another sun, in another galaxy remarkably similar to the Milky Way. There could be another you, living a life nearly identical to yours, reading these very words at this very moment. And not just one such copy, but infinitely many, each with tiny variations. In some of these distant realms, the differences might be trivial. Perhaps you wore a different colored shirt today, or had cereal for breakfast instead of toast. In others, the differences might be more substantial. Perhaps you chose a different career, or live in a different city, or made different choices at crucial moments in your life. But given infinite space and infinite possibilities, every variation that is physically possible must exist somewhere. This is not science fiction or wild speculation. It is a straightforward, logical consequence of an infinite universe with finite arrangements of matter. The idea can feel disturbing because it seems to undermine the uniqueness and significance of our experiences. If there are infinite copies of you, each living slightly different versions of your life, what does it mean to be you specifically? But there is a comforting counterpoint. These duplicate regions would be so unfathomably distant that they are forever beyond our reach. The expansion of space ensures that we could never travel to them, never communicate with them, never even observe them. They exist, perhaps, in a mathematical sense, but they are causally disconnected from us. Your life, your experiences, your choices remain uniquely yours in any practical sense. However, and this is where the subtlety enters the picture, the fact that space appears flat does not definitively prove that the universe is infinite. This is a subtle but critical point that cosmologists emphasize. While measurements show that space has zero or nearly zero curvature on the scales we can observe, it remains possible that the universe curves slightly on scales much larger than our observable horizon. The surface of the Earth seems perfectly flat when you are standing in your backyard. A small triangle drawn on your lawn appears to have angles that sum to 180 degrees. Even a triangle spanning several miles would show no detectable curvature. But if you could measure a triangle large enough, one spanning continents or even the entire globe, you would detect the curvature of the Earth's surface. The curvature is there, but it only becomes apparent when you measure on scales comparable to the size of the planet itself. Similarly, our observable universe, vast as it is, might be too small a patch to detect an overall curvature of the cosmos. If the universe curves back on itself on scales much larger than what we can see, it could be finite in size, yet still have no edge or boundary. And because we can only measure the geometry within our observable horizon, we might never be able to determine the true global shape of the universe. The most intuitive example of a space that is finite but boundless is the surface of a sphere. Think again about a two-dimensional creature living on the surface of a planet. The surface has a definite, measurable total area, making it finite. You could, in principle, measure every square mile of the surface and add them up to get a total. Yet this finite surface has no edge. If you start walking in any direction and keep going in a straight line, you never reach a boundary where the surface ends. You would eventually return to your starting point, having circumnavigated the sphere. Every point on the surface is equivalent to every other point. There is no special location, no center, no boundary. In 3 dimensions, the analogous shape is something called a three-sphere, also known as a hypersphere. This is extraordinarily difficult to visualize because it requires thinking in 4 spatial dimensions, and our brains simply are not wired to do that intuitively. But mathematically, a three-sphere is a perfectly well-defined object. It is the 3-dimensional analog of a 2-dimensional sphere's surface, but existing in 4 dimensions instead of 3. In a universe with the geometry of a three-sphere, space would be finite in volume, but have no boundaries. There would be no edge to reach, no wall to encounter. If you traveled in a straight line long enough, you would eventually return to your starting point, having circumnavigated the entire universe. Of course, the distances involved would be so vast, and the expansion of the universe so relentless that such a journey would be impossible in practice. But in principle, the topology would allow it. Another possibility is that the universe has a shape called a torus, which in 3 dimensions resembles a donut. A flat torus is finite in size, but has no edges. The geometry is locally flat, meaning that small triangles have angles that sum to 180 degrees. But the space connects back on itself in particular ways. Imagine playing an old video game where the screen wraps around. If you move off the right edge, you reappear on the left edge. If you move off the top, you reappear at the bottom. The game world is finite, but it has no boundaries because it connects to itself. A toroidal universe would work similarly, but in 3 dimensions. Travel far enough in one direction, and you would emerge from the opposite direction. The universe would repeat itself, not because there are duplicate regions created by infinite space, but because space wraps around and you encounter the same structures again. In such a universe, if you looked far enough in one direction with a powerful enough telescope, you might actually see the back of your own galaxy from the other side. Though the image would be ancient, showing the galaxy as it was billions of years ago. There are other, even more exotic topologies that are consistent with flat geometry. Space could be twisted or folded in complex ways, creating what mathematicians call multi-connected spaces. These are spaces where there are multiple paths between the same 2 points, paths that loop through the universe in different ways before arriving at the same destination. Cosmologists have searched for evidence of such topologies by looking for repeating patterns in the cosmic microwave background or in the distribution of galaxies. But so far, no such evidence has been found. Current. Observations are not precise enough to distinguish between an infinite flat universe and a finite flat universe with toroidal or other complex topology. Both possibilities are consistent with the measurements we have. The universe may simply be too large for us to ever determine its global shape with certainty. Even if it is finite, it could be so enormous that any curvature or topological features would be undetectable within our observable horizon. Our observable universe might be like a tiny patch on the surface of an immense sphere, so small that the curvature is negligible within our limited view. So where does this leave us? The most honest answer is that we do not know for certain whether the universe is infinite or finite. Both scenarios are compatible with current observations, and each has its own philosophical implications. If the universe is infinite, then it contains an infinite amount of matter and energy. In an infinite universe, every possible arrangement of particles and every possible configuration of matter would not only exist, but would exist infinitely many times. Somewhere out there, infinitely far away, there could be another Earth, almost exactly like ours, with people living lives nearly identical to our own. In fact, in an infinite universe, there would be infinitely many such copies, each with slight variations. This is not science fiction, but a logical consequence of infinity. If space goes on forever and is filled with matter, then given enough distance, every possible arrangement must repeat. The atoms that make up you, me, and everything around us are finite in number and type. They can only be arranged in so many ways. In an infinite universe, those arrangements would recur endlessly across the vastness of space. This idea can feel unsettling or wondrous, depending on your perspective. It means that the uniqueness we feel, the sense that our lives and experiences are singular, would be true in a local sense, but not in a cosmic sense. Yet the nearest such copy would be so unfathomably far away that light from it could never reach us, even given infinite time because of the expansion of space. These parallel regions would be forever beyond our causal horizon, existing in a realm we can reason about mathematically, but never observe directly. On the other hand, if the universe is finite, it raises different questions. A finite universe would have a specific volume and a specific amount of matter and energy within it. In such a universe, the arrangements of particles would not infinitely repeat. There would be only one of each particular configuration, making each arrangement, including us, unique in the truest sense. But a finite universe also prompts us to ask, if the universe has a finite size, what lies beyond it? Here is where our intuition leads us astray. The question assumes that beyond the universe there is something, even if it is empty space. But according to general relativity, space itself is part of the universe. There is no space beyond the universe. The universe is not embedded in some larger void. Asking what lies beyond a finite universe is similar to asking what is north of the North Pole. The question is based on a misunderstanding of what the universe is. Space and time themselves are properties of the universe. They do not exist independently of it. A finite universe simply means that space is self-contained, curving back on itself in such a way that there is no outside. This is profoundly counterintuitive because our everyday experience tells us that every volume of space must be inside something else. But the universe plays by different rules. The expansion of the universe adds another layer to this mystery. We know from observations that the universe is expanding. Galaxies are moving away from each other, and the farther apart two galaxies are, the faster they recede from one another. This is not because galaxies are moving through space like cars on a highway. Instead, space itself is stretching. The fabric of the cosmos is growing, carrying galaxies along with it. This expansion has been happening since the Big Bang, approximately 13.8 billion years ago. But what is expanding? If the universe is infinite, then an infinite space is becoming even more infinite, which sounds paradoxical. Yet, mathematically, it makes sense. Imagine a number line extending to infinity in both directions. Now, imagine stretching the number line so that the space between each number doubles. The line is still infinite, but the distances within it have increased. An infinite universe can expand in precisely this way. If the universe is finite, then expansion means the volume of space is growing over time. A finite, curved universe would become larger with each passing moment. Either way, the expansion does not require an outside space into which the universe expands. The universe itself is everything, and its expansion is an intrinsic property of space. The expansion of the universe also affects what we can see. Because space is stretching, distant galaxies are receding from us at tremendous speeds. Galaxies more than a certain distance away are receding faster than the speed of light. This does not violate relativity because they are not moving through space faster than light. Space itself is expanding, carrying them with it. The result is that there are galaxies whose light will never reach us, no matter how long we wait. They lie beyond what is called the cosmic event horizon, a boundary that divides the universe into regions we can potentially observe and regions forever beyond our reach. As time passes, more and more galaxies cross this horizon, disappearing from view. In the distant future, as the expansion of the universe accelerates, observers on Earth, or whatever remains in our vicinity, will see fewer and fewer galaxies. Eventually, only the galaxies in our local gravitational group will be visible. The rest of the universe will have receded beyond the horizon, their light redshifted to nothingness. Future astronomers, if they exist, might look out and see only darkness beyond their local cluster, unaware of the vast cosmos that once filled their sky. This accelerating expansion is driven by something called dark energy, a mysterious component that permeates space and pushes it to expand ever faster. Dark energy makes up about 71% of the total energy content of the universe, yet we know almost nothing about what it actually is. Its presence is inferred from observations that distant supernovae are dimmer than they should be if the universe's expansion was slowing down. Instead, the expansion is speeding up, which was a shocking discovery when it was first confirmed in the late 1990s. Two independent teams of astronomers studying distant Type 1a supernovae, incredibly bright stellar explosions that can be seen across vast cosmic distances, found that these supernovae were further away than expected based on their brightness. This could only mean that the universe's expansion had accelerated over time, driven by some unknown force pushing space apart. The discovery of dark energy was so unexpected that it took the scientific community some time to accept. It ran counter to expectations. Astronomers had assumed that gravity would slow the universe's expansion over time, as all the matter in the universe pulled on all other matter. The question was thought to be whether there was enough matter to eventually halt and reverse the expansion, causing the universe to collapse back on itself in a big crunch, or whether the expansion would continue forever but gradually slow down. The idea that the expansion might be speeding up was not even on the table. But the data was clear, and both teams independently reached the same conclusion. The universe's expansion is accelerating. Something is counteracting gravity, pushing space apart with ever greater force. This mysterious something was named dark energy, though the name is really just a placeholder for our ignorance. We call it dark because we cannot see it directly, and we call it energy because it seems to be a property of space itself, a kind of energy density associated with the vacuum. Dark energy is fundamentally strange. Unlike matter, which dilutes as space expands, because the same amount of stuff gets spread out over a larger volume, dark energy appears to have a constant density. As the universe expands and the volume of space increases, the total amount of dark energy increases proportionally. If space doubles in size, the amount of dark energy doubles as well, maintaining the same density per unit volume. This means that as time goes on, dark energy comes to dominate the universe more and more. In the early universe, when everything was much closer together, the density of matter and radiation was high enough that dark energy was negligible. But as the universe expanded, matter diluted, while dark energy remained constant, and eventually, dark energy took over as the dominant component of the cosmos. Dark energy complicates the question of the universe's size and shape. If the universe is infinite, dark energy pervades all of that infinite space. If the universe is finite, dark energy determines how its expansion will evolve over time. In either case, dark energy ensures that our observable universe is just a small, ever-shrinking fraction of the whole, at least in terms of what we can see and potentially reach. The nature of dark energy is one of the greatest mysteries in modern physics. Is it truly a property of empty space, a cosmological constant, as Einstein once proposed and then abandoned? Or is it a dynamic field that varies over time and space? Could it be a sign that our theory of gravity, general relativity, breaks down on cosmological scales and needs to be modified? These questions remain open, and answering them is a major goal of contemporary cosmology. One intriguing possibility, suggested by some theories, is that dark energy might not remain constant forever. If dark energy strengthens over time, the universe could eventually be torn apart in an event called the Big Rip. In this scenario, the accelerating expansion would become so violent that it would overcome all the forces holding structures together. First, galaxy clusters would be ripped apart, then galaxies themselves, then solar systems, then planets, and finally, atoms themselves would be torn asunder as space expanded faster than even the electromagnetic force could hold electrons to nuclei. The universe would end not in fire or ice, but in a catastrophic disintegration of all structure. Alternatively, dark energy might weaken over time, allowing the expansion to slow and eventually reverse. The universe could collapse back on itself in a big crunch, all matter and energy converging back to a point of infinite density, possibly to bounce back in a new Big Bang, creating a cyclic cosmos that expands and contracts eternally. Or, dark energy might remain constant, leading to a big freeze or heat death, where the universe continues expanding forever, gradually cooling and diluting until all stars have burned out, all black holes have evaporated through Hawking radiation, and nothing remains but a thin, cold soup of elementary particles separated by vast gulfs of empty, expanding space. These scenarios, speculative as they are, remind us that the universe has a history and a future. It began in a hot, dense state nearly 14 billion years ago. It has evolved through eras of radiation domination, matter domination, and now dark energy domination. And it will continue to evolve, its fate determined by the properties of dark energy and the overall geometry and content of space. Whether that future is infinite in duration, as current evidence suggests, or whether time itself might end in some cosmic catastrophe, we do not yet know. But for tonight, for this moment, these deep questions about the ultimate fate of the cosmos can rest. They are part of the grand mystery, the vast, unknowable future that stretches ahead. What matters now is the present, the here and now, the simple fact that we exist within this remarkable universe, able to ponder its nature and contemplate its immensity. The universe, whether infinite or finite, whether destined for endless expansion or eventual collapse, is here with us now. It is the stars shining above, the earth beneath our feet, the air we breathe, the matter that makes up our bodies. We are part of it, woven into its fabric, temporary patterns in the great cosmic dance. The concept of the multiverse introduces yet another possibility, one that extends the question of the universe's size into even more speculative territory. According to some versions of inflationary cosmology, the theory that describes a brief period of exponential expansion in the early universe, our observable universe might be just one bubble among countless others in a much larger cosmos. Inflation was proposed in the early 1980s by physicist Alan Guth and independently developed by others, including Andre Linde and Andreas Albrecht. The theory was created to explain certain features of the universe that were difficult to account for in the standard Big Bang model. One puzzle was the horizon problem. Why does the universe look essentially the same in all directions, even in regions that are so far apart that light has never had time to travel between them since the Big Bang? How did these widely separated regions come to have the same temperature and properties if they could never have interacted? Another puzzle was the flatness problem. Why is the universe so remarkably close to being geometrically flat? In the standard Big Bang model, any tiny deviation from perfect flatness in the early universe would have been amplified over time, leading to a universe that was either dramatically curved or that collapsed or expanded so rapidly that no structures could form. Yet, we observe a universe that is flat to extraordinary precision. This fine-tuning seemed to require special initial conditions that appeared highly improbable. Inflation solves both these problems elegantly. During inflation, which lasted only a tiny fraction of a second shortly after the Big Bang, the universe expanded at a phenomenal rate, growing from something smaller than an atom to something much larger than the observable universe today. This rapid expansion stretched space smooth, ironing out any initial irregularities and making the universe appear uniform on large scales. It also drove the geometry toward flatness, just as inflating a balloon makes its surface appear flatter and flatter as it grows larger. A small patch of even a highly curved universe would appear flat if expanded sufficiently. Inflation explains the horizon problem because regions that now appear to be widely separated and unable to communicate were actually in close contact before inflation began. They came to equilibrium, reaching the same temperature and properties, and then inflation stretched them far apart. It explains the flatness problem, because inflation automatically drives the universe toward a flat geometry, regardless of what the initial curvature might have been. The evidence for inflation comes from multiple sources, most notably the detailed patterns observed in the cosmic microwave background. Inflation predicts specific features in the distribution of temperature fluctuations, and these predictions match observations with remarkable accuracy. The theory has become a cornerstone of modern cosmology, widely accepted as the best explanation for the large-scale properties of the universe we observe. But some models of inflation suggest that once inflation starts, it does not end everywhere at once. Instead, inflation ends in some regions while continuing in others. Each region where inflation stops becomes a bubble universe, like ours, with its own Big Bang and its own expansion history. Meanwhile, the regions where inflation continues keep expanding and spawning new bubble universes indefinitely. This is called eternal inflation, and it leads to the idea of an infinite multiverse. In the eternal inflation scenario, our universe would be one bubble among an infinite number of bubbles, each potentially with different physical properties. The laws of physics, the values of fundamental constants, even the number of dimensions of space, might vary from one bubble to another. The properties that make our universe hospitable to life, such as the strength of gravity, the mass of the electron, or the amount of dark energy, might be mere accidents, random outcomes from an infinite collection of possibilities. Some bubbles might be hospitable to life, while others might be cold, sterile voids where no complexity can arise. Most would never interact, separated by vast regions of still inflating space. This multiverse idea is highly speculative and remains controversial among physicists. It is difficult to test because, by definition, other bubble universes would be beyond our observable horizon, causally disconnected from us. We could never see them, or visit them, or communicate with them. Some scientists argue that a theory that predicts unobservable entities is not scientific, that it crosses the line from physics into metaphysics. Others contend that if a theory makes testable predictions within our universe and happens to predict a multiverse as a side effect, then the multiverse is a legitimate scientific idea, even if we cannot observe it directly. One intriguing possibility is that two nearby bubble universes might collide, and such a collision could leave detectable imprints in the cosmic microwave background radiation. When two bubbles expanding through space intersect, the collision would create a disturbance, a shock wave propagating through the fabric of each bubble. If our bubble had collided with another in the distant past, this collision might have left a circular pattern or other anomaly in the temperature map of the microwave background, like a bruise on the surface of the cosmos. Researchers have searched for signs of such collisions, looking for patterns that might indicate our bubble universe once bumped into another. The searches involve sophisticated statistical analyses of the cosmic microwave background, looking for deviations from the expected patterns. So far, no such evidence has been found. The microwave background appears to match the predictions of single bubble inflation without the need for collisions. But the search continues, and future observations with more sensitive instruments might reveal signs of a multiverse, if it exists. The multiverse also offers a potential explanation for why the universe seems so finely tuned for life. The fundamental constants of nature, such as the strength of gravity or the mass of the electron, have values that appear precisely calibrated to allow stars, planets, and ultimately life to exist. If these constants were even slightly different, the universe would be a vastly different and likely lifeless place. This apparent fine-tuning has puzzled scientists and philosophers for decades. In a multiverse with an infinite number of bubble universes, each with different physical laws and constants, fine-tuning is no longer mysterious. Most bubbles would be inhospitable to life, but a tiny fraction would have conditions just right for complexity to emerge. We find ourselves in one of those rare bubbles simply because those are the only places where observers like us can exist. This is known as the anthropic principle, the idea that the universe appears fine-tuned because we are here to observe it. In universes where the constants were unfavorable, no one would be around to wonder why. Whether the multiverse exists or not, whether the universe is infinite or finite, whether it has an edge or curves back on itself, these questions probe the deepest nature of reality. They force us to confront the limits of what we can know and observe. They remind us that the cosmos is far stranger and more wondrous than our ancestors could have imagined. Ancient cosmologies placed Earth at the center of everything, with the stars and planets revolving around us on crystalline spheres. The universe was small, comprehensible, human-scaled. As our understanding grew, we discovered that Earth is just one planet among many, orbiting an ordinary star in the outskirts of an ordinary galaxy. Then we learned that our galaxy is one of billions, and those billions are spread across a space so vast that light takes billions of years to cross it. Now we contemplate the possibility that even this immense cosmos might be just a fragment of something even larger, perhaps infinitely larger. The scale of the universe, whether finite or infinite, dwarfs human comprehension. Yet here we are, tiny beings on a small world, capable of pondering these immense questions. We have built instruments sensitive enough to detect the faint whisper of the Big Bang, telescopes powerful enough to see galaxies formed when the universe was young. We have devised mathematics elegant enough to describe the curvature of space and the dynamics of cosmic expansion. This capacity for wonder, for curiosity, for asking questions that stretch beyond the immediate and the practical, is one of the most remarkable features of the human mind. We do not need to know whether the universe is infinite to live our daily lives. Yet we ask anyway, driven by a desire to understand our place in the grand scheme of things. The question of whether the universe has an edge is also a question about boundaries in general. We are used to boundaries in our lives. We experience beginnings and endings, arrivals and departures. We understand stories because they have structure, a clear arc from start to finish. But the universe might not conform to these narrative expectations. It might be fundamentally boundaryless, a reality without beginning or end in space, and possibly in time as well. Some cosmological models suggest that the Big Bang itself might not have been the absolute beginning. The universe could have existed in some form before the event we call the Big Bang, perhaps cycling through infinite expansions and contractions, or existing in a state we cannot yet describe. The concept of time itself becomes murky when we approach the moment of the Big Bang. General relativity predicts that time and space emerge together at that moment. So, asking what came before is like asking what is south of the South Pole. The question assumes a framework that does not apply. Yet physicists continue to probe these ultimate questions, seeking a theory of quantum gravity that would unify general relativity with quantum mechanics, and perhaps provide a more complete picture of the universe's origin. Such a theory might tell us whether the universe truly had a beginning, or whether it is part of an eternal structure beyond our current understanding. In the meantime, we live with uncertainty. The universe may be infinite, or it may be finite but boundless. It may be one of many in a multiverse, or it may be all there is. These are not idle philosophical musings. They are questions at the frontier of science, informed by cutting-edge observations and sophisticated theory. They remind us that for all we have learned, the universe retains its capacity to surprise and mystify us. There is something comforting in this vast uncertainty. It means that no matter how much we discover, there will always be new mysteries to explore, new frontiers to investigate. The universe, in its grandeur, offers an endless source of wonder. It invites us to look up, to question, to imagine possibilities beyond our immediate experience. As you lie here tonight, letting these thoughts wash over you, consider the remarkable fact that you are part of this vast cosmos. The atoms in your body were forged in the cores of stars that burned and perished long before the Earth was formed. You are made of stardust, quite literally, connected to the universe in the most intimate way. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces and scattered across space when those stars reached the end of their lives. The energy that animates you, that allows you to think and feel and wonder about the universe, comes ultimately from the sun, which fuses hydrogen into helium in its core, releasing light that travels across space to warm the Earth and power the chemistry of life. You are a temporary arrangement of matter and energy, a pattern that has arisen in the universe and will one day disperse back into it. But while you exist, you have the privilege of contemplating the whole. The universe does not need us to understand it. Stars burn, galaxies collide, space expands, all without regard to whether anyone is watching. Yet here we are, observing and thinking and asking questions. We have looked back in time to the cosmic microwave background, the earliest light we can see. We have measured the expansion of space, charted the distribution of galaxies, and calculated the fate of the cosmos billions of years hence. We have accomplished all this in just the past century, an eye blink in cosmic time. What will we learn in the next century, or the next millennium, if we survive and continue to explore? Perhaps we will find definitive evidence that the universe is infinite. Or we might discover subtle signs of curvature that reveal a finite cosmos. We might even detect hints of other universes beyond our own, collisions or quantum entanglements that betray the presence of a multiverse. Or we might find that the ultimate nature of reality is something we have not yet imagined, something so strange and unexpected that it overturns our current understanding entirely. Science is an ongoing process, a journey rather than a destination. Each answer leads to new questions. Each discovery reveals new mysteries. The universe is not a puzzle to be solved once and for all, but an infinite source of wonder that grows richer the more we learn. Even if we never definitively answer whether the universe is infinite or finite, the act of asking, of investigating, of pushing the boundaries of knowledge is profoundly meaningful. In a way, the question itself reflects something deep about human nature. We are finite beings trying to comprehend the infinite. We live brief lives, a few decades at most, yet we ponder the age and fate of a cosmos that has existed for nearly 14 billion years and will continue for trillions more. We are confined to a tiny planet, yet we reach out with telescopes and mathematics to grasp the structure of the entire universe. This tension between our limitations and our aspirations is part of what makes us human. The ancient philosophers, who wondered whether the universe was infinite or finite, were asking the same fundamental question we ask today. Though our tools and knowledge are vastly different, they had no telescopes, no understanding of atoms or stars or the expanding universe. Yet they thought deeply about the nature of existence, using logic and imagination to explore possibilities. In their own way, they were doing science. Seeking to understand the world through reason, we stand on their shoulders, inheritors of a long tradition of curiosity and wonder. Every generation adds to the accumulated knowledge, refining our understanding bit by bit. The universe reveals itself slowly, reluctantly, through patient observation and careful thought. We have come so far, yet the horizon of the unknown remains vast, and that is as it should be. A universe fully understood, with no mysteries left to explore, would be a lesser place. So, tonight, as you close your eyes and let sleep carry you away, take comfort in the grandness of it all. You are part of a universe so immense that it might have no edge, so ancient that it has had time for stars to be born and perish countless times over, so rich in structure that it contains billions of galaxies, each home to billions of stars. You are connected to it all, made of the same substance, governed by the same laws, part of the same story. Whether the universe is infinite or finite, whether it has an edge or curves back on itself, it is vast beyond comprehension and beautiful beyond words. It has given rise to stars and planets, to life and consciousness, to beings like us who can look back at the universe and marvel. The cosmos is not cold or empty or meaningless. It is full of light and matter and energy, full of processes and patterns, full of possibilities. As you drift towards sleep, let your mind wander among the galaxies. Imagine the light from distant stars traveling across the void, photons that left their source millions of years ago, finally arriving at your eyes, connecting you across space and time to suns that may no longer exist. Think of the cosmic microwave background, that faint glow from the early universe, surrounding us on all sides, a whisper from the dawn of time. Picture the expanding universe, space itself stretching, carrying galaxies apart, the distances between them growing with each passing second. Imagine the dark energy that drives this expansion, an invisible force pervading every cubic centimeter of space, pushing the cosmos toward a future we can only dimly foresee. Think of the possibility, however speculative, that beyond our horizon lie other universes, other realms of existence, each perhaps with its own laws and structures. All of this exists, whether or not we can see it. The universe is there, vast and magnificent, filled with wonders we have discovered and countless more we have yet to imagine. You are a part of it, a conscious fragment of the cosmos, experiencing itself, thinking about itself, marveling at itself. In the grand scheme of things, our individual concerns, our daily worries and fears are fleeting. The universe carries on, indifferent to our struggles. Yet there is solace in this perspective. The problems that loom large in our minds are small against the backdrop of cosmic time and space. We are here for a brief moment, and that moment is precious precisely because it is temporary. So rest easy. The universe does not ask you to solve its mysteries tonight. It does not require you to understand infinity or to grasp the shape of space. It simply asks you to exist, to experience, to be part of the unfolding story. And you are doing that beautifully. Just by being here, just by breathing, just by letting your thoughts float among the stars. The question of whether the universe has an edge will remain, perhaps forever at the boundary of what we can know. But that is fine. Some mysteries are meant to inspire rather than to be solved. The universe invites us to wonder, to dream, to reach beyond ourselves. It offers a perspective that humbles and elevates us at the same time. You are lying here, on a planet that orbits a star, in a galaxy that is part of a vast web of galaxies, in a universe that may be infinite or may be finite, but either way is far grander than we can fully comprehend. You are made of stardust, powered by the same forces that light up the cosmos, connected to everything that has ever been or ever will be. And for tonight, that is enough. You do not need to solve the mysteries of existence. You do not need to know whether the universe has an edge. You only need to rest, to let the day fall away, to allow sleep to carry you into dreams. The universe will still be here in the morning, vast and beautiful, filled with wonders waiting to be discovered. So, close your eyes, feel the weight of your body against the bed, the slow rhythm of your breathing, the gentle pull of sleep. Let the questions fade. Let the vastness of space become a comforting presence rather than an overwhelming concept. Let the universe cradle you in its infinite or finite arms, either way embracing you as one of its own. You have done enough for today. You have thought and wondered and learned. You have reached across billions of light years with your mind, contemplating the edges of existence or the boundless expanse of infinity. You have stood at the frontier of human knowledge and looked out into the unknown. That is a beautiful thing. Now it is time to rest. The stars will continue to burn. The galaxies will continue their slow dance through space. The universe will continue its expansion, all while you sleep. And when you wake, it will all still be there, waiting for you to wonder again. The universe is patient. It has been here for billions of years before you, and it will be here for billions of years after you. Your moment within it is brief, but precious. You are a way for the universe to know itself, a pattern of atoms and energy that has become conscious, capable of asking why and how and what if. So sleep now. Let your thoughts dissolve like stars fading in the dawn. Let the questions rest until another day. The universe does not have all the answers, and neither do you, and that is perfectly fine. The mystery is part of the beauty. The cosmos is vast. It may be infinite, stretching forever without boundary. It may be finite, curving back on itself in ways we can barely imagine. Either way, it is home. It is all we have, and it is more than enough. Rest your mind. Feel the gentle pull of sleep. Know that you are part of something magnificent, something that transcends understanding but invites wonder. You are here, now, in this moment, under the same sky that has watched over Earth for billions of years, connected to the same universe that gave birth to everything we know. And as you drift away into sleep, let this be your final thought. The universe, infinite or finite, edged or boundless, is here with you. You are not separate from it. You are woven into its fabric, a thread in the grand cosmic cloth, temporary but real, small but significant. The stars are shining, the universe is expanding. Space curves or extends, finite or infinite, and all of it is beautiful. All of it is home. Sleep now. Dream of galaxies and light, of space and time, of mysteries that inspire rather than trouble. Let the vastness hold you gently. Let the cosmos sing you to sleep with its ancient, silent song. You have done enough. You are enough. The universe asks nothing more of you tonight than to rest, to dream, to be. Close your eyes. Breathe deeply. Let go. The universe has no edge, or it has an edge we cannot see, or it curves back on itself in impossible dimensions. It does not matter which. What matters is that you are here, part of it all, held in the embrace of space and time and matter and energy, connected to everything that ever was or will be. Rest now. The cosmos will keep its vigil while you sleep, and when morning comes, when you open your eyes again, the stars will still be there. The universe will still be vast, and you will still be a part of something magnificent beyond measure. Sleep well. Dream gently. Let the infinite or finite universe carry you softly through the night, a temporary pattern in an eternal or bounded dance, brief but beautiful, small but precious. Good night. The universe is with you, now and always, in dreams and waking, in questions and wonder, in the vast silence of space where light travels for billions of years just to touch your eyes. Good night.